Introductory quantum mechanics often analyzes particles in perfect isolation, a solitary electron in a potential well, or a single photon traveling freely through a vacuum. While these isolated models provide a theoretical baseline, they are insufficient for applied physics. The phenomena that drive modern technology rely entirely on the interactions between different species of particles. For example, the coherence of a laser requires an intense exchange of energy between photons and the internal states of atoms. Similarly, solar power relies on photons striking electrons to create the mobile charge carriers that form an electrical current. To engineer these systems, physicists require a unified mathematical language to describe the exact moment different particles exchange energy and momentum. In advanced physics, particles are no longer treated as permanent objects, but as excitations within a field. This means interactions can be modeled by accounting for the continuous creation and destruction of these excitations. This accounting is performed by creation and annihilation operators. The operator with the dagger creates a fermion in state I, while the operator without it annihilates one. This operator algebra provides a direct link between the microscopic scale of a single particle event and the observable properties of macroscopic systems. Particles divide into two classes, fermions, like electrons, and bosons, like photons. Fermion operators obey anticommutation relations, enforcing Pauli exclusion so a state holds only 0 or 1 particle. Boson operators obey commutation relations, allowing any number of particles to share the same state simultaneously. Because these species are distinct, their operators commute. As the equation shows, creating or destroying a photon does not directly violate the underlying algebra of the electron system. These abstract statistical rules, exclusivity for electrons and communality for photons, set the physical boundaries for every system they populate. A physicist maps the energy of a system using the total Hamiltonian equation. The interaction Hamiltonian is the specific component that dictates how energy is exchanged between matter and the surrounding field. To deconstruct optical absorption, the boson annihilation operator A removes a single photon. Simultaneously, the fermion operator Cg destroys the electron in its lower ground state. Finally, the fermion creation operator recreates the electron in a higher excited state, yielding an updated overall state vector. What we perceive as light absorption is fundamentally this sequence of mathematical bookkeeping, where created and destroyed quanta are balanced across the system. Emission introduces an asymmetry. Applying the bosonic creation operator yields a probability factor proportional to the square root of n plus 1. The n variable drives stimulated emission. The probability of an atom emitting a photon scales with the photons already present in that mode. This scaling mechanism allows lasers to multiply photons within a single quantum mode, producing high-intensity, coherent light. However, the +1 part of the factor ensures that emission can occur even when 0 photons are initially present. This explains why an excited atom can decay spontaneously by coupling to the quantum vacuum. Through this algebra, we see that spontaneous and stimulated emission are not separate physical rules, but two unavoidable consequences of bosonic creation. These operator interactions happen instantaneously. To bridge the gap to laboratory measurements, physicists must translate these events into transition rates. This is typically done using Fermi's golden rule, calculating the probability of a weak interaction occurring over time. The probability hinges on the transition matrix element. If it evaluates to 0, the physical transition is strictly forbidden, regardless of energy available. This calculation provides the baseline for predicting transitions across diverse systems, from photon absorption in a gas to electron tunneling in a transistor. By mapping these interacting operators against the density of available states, physicists can calculate exactly how a material will respond to external fields or internal vibrations. This framework is highly adaptable. Moving from light to solid-state physics, we swap the photon operator for a phonon. This yields the electron-phonon interaction term, HCk-Q daggered, HCk, HBq daggered. Here, an electron wave emits a phonon, diverting its original momentum onto a new path. This microscopic deflection is the physical source of electrical resistance in copper wires and semiconductors. As the logic chain indicates, higher temperatures generate more phonons, which triggers more scattering events and increases the measured electrical resistance. Whether the system is an emitting OLED, a cooling superconductor, or a high-speed microchip, the underlying mechanics remain consistent. From the glow of an atomic lamp to the resistance in a wire, every physical exchange is the result of this rigorous bookkeeping, quanta being created and destroyed across the quantum fields.